Well, good evening, good afternoon, if we have any attendees from the US, and welcome to the webinar of tonight. My name is Ruben Wansink, and I'm a board member of the Department Amsterdam and of the KNVTS, which is the Royal Dutch Association of Maritime Industry Engineers. And today I'm honored to host this webinar. And the KNVTS hosts webinars every month about technical topics related to our industry, and we share these by mailings and on LinkedIn. Practicalities: today the webinar will be approximately 50 minutes, so 50, and the presentation that will be done by Laurent will take about 35 to 40 minutes. And at the end, we will have time to do questions. Your microphones are muted and your cameras are off. There is a chat function and a question function which you can use to ask questions. I will then read them and Morel will answer them. In case we have too many questions, we will please understand that we cannot keep on going, so we will treat them later on and Laurent can then answer them by email. So today we have the honors to have Laurent Morel, who is next to me on the screen, and he has a master's degree in aerospace engineering. He has been active in the maritime industry for almost 20 years, which is 3 more years than me. We have been dealing with each other once in a while here and there in different countries, and he is the manager operations at InfraCore Company, and they have applications based on worldwide patented, easy, scalable technology for lightweight, heavy-duty, damage-tolerant, load-bearing applications made from FRP material. He is also board member of Composites NL, the Dutch Composite Association. So, without further ado, I'm going to give the floor to Laurent. Laurent, welcome, and please share your screen.
Thank you so much, Ruben. Good evening, everybody. Indeed, my name is Laurent Morel, and I want to, first of all, thank you, KNVTS, for this beautiful opportunity. And I want to take you along the technology and a number of projects that we have been working on for the last couple of years. So it's not the only thing what we are doing. I'm just focusing on the number of those. Let me increase my screen so that's better visible. So first of all, I want to explain you a bit about our patented technology, because we have a specific composite technology. I want to illustrate what our sister company FiberCore Europe has been doing for the last couple of years in the infrastructural applications. Then I will skip or shift to InfraCore Company, which is the company I'm working for, and then zoom in on the number of projects, mainly a full composite SOLAS ship, so a seagoing full composite ship of 85 meters, a rudder flap that we have developed for the larger container ships, so 18,500 TEU. And then I will also elaborate a bit on a development that I've been working on recently, a full composite inland barge. So as Ruben indicated, indeed, we are in the heavy-duty load-bearing composite structures. And what you see here are a number of bridges. On the lower left, you see the world's largest composite lock gates, which I will show later on as well. And then to the right, bottom right, the second picture from the left on the bottom, that's a helideck that we did for the bigger yacht of Steven Spielberg. So we have already also a number of applications on board of real ships. So as stated, I will start with FiberCore Europe. What is FiberCore Europe? Focusing on bridges and locates. And they have their own production facility in Rotterdam. And they are really pioneers in the composite bridge world. And they have been doing that since 1996. So how many bridges? Let me see. They have delivered more than 1,200 bridges already in the last couple of years. And these bridges go from the lighter class, so the pedestrian bridges, all the way up to the heaviest load class, so the 60-ton class bridges for the heavy traffic. InfraCore IP is another company within the InfraCore holding. That's where all the patents are stored. And we have patents on the way how we place fabrics in the products. We have patents on the way of infusing those fabrics, so how the resin is introduced into the end product. And we also have patents on the mold system, because it's kind of interesting to mention that these 1,200 bridges have been built on the same mold, so the mold costs are in the most cases out of the commercial equation, which brings me to the first bold statement of tonight. It's a fact that composite materials are more expensive than the conventional maritime products such as steel, but FiberCore Europe is cost competitive purchasing wise with their composite bridges as compared to wood, concrete or steel. And one of the reasons is because the mold system is out of the commercial equation, and there are other reasons which I will elaborate on during the course of this presentation. What you see here is the basic technology, how the fabrics are placed. And we have solved, that's the second statement of tonight, we have solved one of the biggest challenges of the composite world, namely delamination, which means that a crack can propagate between layers, which can also happen with us. But we have made delamination inconsequential because it cannot grow further than a certain extent. And I will explain that also in a few slides. So a heavy impact can take place on our products, followed by fatigue. It will definitely lead to local delamination, but the damage cannot grow as it could and would with other composite technologies. Important to mention is that indeed our patented technology is used by our sister company FiberCore Europe, but it's also readily available under licensing agreements. And we have already a number of licensing agreements with partners everywhere in the world. So that could also be the case for you. So the technology is available under licenses to whomever is interested in it. So I stated that fatigue after impact will lead to local delamination, but it cannot propagate. That's not only a theoretical statement, it has been proven and validated, and it has been witnessed by DNV. What you see here is a 60-ton traffic bridge, which has been seriously impact damaged and has been put then into a fatigue cycle of 120 years, so 30 million cycles. And we have proven that the delamination, because of this local impacts, has not propagated, has not grown, which has led to the statement by classification societies that this bridge could be installed without repair for a remaining lifetime of 50 years. So that's kind of, I'm super proud of being capable of saying that a bridge can be seriously damaged, put into fatigue cycle for 120 years, and can be installed without repair with a remaining lifetime of 50 years. So these are the typical pictures that most of the people have when they think of composites. It's an amazing material, but once it fails rapidly. So think of wind turbine blades that just collapse globally because of fatigue, or ships that have been subjected to slamming loads and just delaminate completely. That cannot happen in this extent with our technology. So again, our technology has a serious track record. So more than 1,200 heavy-duty structures have been realized. We are very cost effective. We are damage tolerant with an extreme robustness. Last but not least, also one of the weaknesses of composites is that it fails fast under fire. We have an excellent structural load capacity under fire, which I will also demonstrate later on. And also we are cheaper, lighter and cheaper than the conventional sandwich composite structures, which I also will explain during the course of this presentation. Did we invent something? Definitely. Was it inspired by nature? Certainly. What you see here is actually an oblique layered structure, what you can see with fishes, sharks, bugs, rhinoceroses, even in our hair structure. And we have actually the same basic principle in our composite technology. What you see here are typical composite approaches. On the upper left, you see a classic sandwich structure consisting of two facings with in the middle a structural core. And this red arrow is showing that if a crack would propagate there between the layers, it would just continue grow and grow and grow and growing. On the upper right, you see a typical pultruded box assembly. And this approach has been extensively applied in the US, for instance, in bridge building. And all these bridge-like structures have failed in a couple of years. So again, the red arrow is showing that if a crack starts to propagate between these pultruded beam profiles, it just can continue on growing. And in the middle, you have a blend between the two approaches, which is actually, again, a pultruded box assembled structure, but then surrounded by facing structures. And these red arrows, again, are showing potential crack growth path. And if it goes, it goes. And on the bottom, that's our approach. Our approach, is it complex? No, it's basic, but it's very clever. And it's also understandable for our steel designers, our steel engineers. I start on the upper left, where you see a classic steel I-beam. And if you would morph that to the lower left profile, so this Z steel beam, it has the same structural properties as the I-beam, it only has been morphed. And what we did is we translated this Z profile into the upper right composite profile, which is identical. It has identical material properties in all directions. But if you want to morph that to have dedicated material properties in a particular direction, you go to the lower right and you just add fibers in a particular direction. So what we did is we started with the classical I-beam, morphed it to a Z, and we add additional strength and stiffness in the directions that the end application needs. So we start with this basic Z layer. We add additional material where deemed necessary, and we just continue stacking those fabric beams. For me, it's very important that you understand that these fabric beams in this phase are not consolidated. These are dry fabrics that are placed into a mold in a very fast and efficient way before being frozen in their end geometry by injecting resin. In order to be able to stack these preforms, you have between these perpendicular webs, you have non-structural foam. So we take in the first step of our production phase, we take a foam preform, we wrap it, we surround it with dry fabrics, then we go to the mold and we stack these preforms next to each other. And once the product is consolidated, so it has been injected with resin, and you would impact it as I just did, and you would then fatigue it. This is just showing how a fatigue cycle would look like by driving over it with a wheel, but it could be hogging and sagging because of a ship. This local damage cannot grow any further than the overlap that you see in each preforms. So again, you see this local impact attacking this vertical web, but there's plenty of remaining material around it, surrounding it, to transfer the loads. And you could think that, okay, this is a nice way of doing that. So you have these inner stiffeners in a certain direction. But what if you need shear stiffeners in the other direction? Then instead of working with a standard non-structural foam block as core material, you would work with these little blocks which have been surrounded by fabric in order to have webs in the other direction. So we can definitely work with webs in perpendicular directions, the main webs. And if you need even more strength, instead of using a non-structural foam block, you could work with a full composite monolithic block, which enables us to first of all transfer massive forces in the out of plane direction, but it also helps us drill, for instance, holes wherever deemed necessary. So you could attach an engine foundation as an example just by drilling holes in these monolithic blocks. So what I'm trying to say is we can place webs in each direction as we want. If deemed necessary locally, we go for a full reinforcement, which enables us a lot of flexibility in the design, in the production, and in the outfitting eventually. So this is, I think, the best illustration of our technology, where you have these overlapping layers, which enables us to avoid this global crack growth propagation, which would lead to delamination. We can add webs in every direction as deemed necessary, and we can make structures going from, let's say, a height of 4 centimeters all the way up to what we did actually already. We could go further, but we went already to structures with a height of 3 meters. So we can make very slender products, but we can also make very high products. And the suggestion could be that we only make flat products, but later on we will show that we can also make curved structures, and even hydrodynamic profiled structures like rudder flaps. So that was about the fabric technology. Then I would like to focus on the size, the sheer size of the products, because another aspect of our patented technology is the resin infusion. So the way we inject our products, and that's a modular technology. So for us, it's kind of irrelevant how large the product is, because the resin infusion strategy is modular. So whether it's 1 square meter and I charge a bit 1 square kilometer, for us it's the same building block approach, and it's just a matter of scaling it up. What you see here is a 60-ton traffic bridge. What you see here is a 142-meter bridge, which is a hybrid bridge. So the vertical steel trusses, are there, and the road you drive on, that's our InfraCore bridge. So we also make hybrid applications. So how to assemble composite to composite or composite to steel, we have that knowledge in-house. Nice anecdote is the composite and the steel of this bridge was assembled on site next to the highway in the middle of the winter. It was freezing cold, and the bridge was placed on its final position in 2 times 4 hours. So the composite technology has definitely advantages in way of robustness, but it's also lightweight, and it enables benefits, facilitates benefits in the mounting and in the transporting, and I will come back to that later on. This is a nice example of the size of our product, but also, yeah, it's relatively lightweight. So you can still transport this massive plate on a bridge in this position. And these bridges are so lightweight that they are buoyant. So there are places where it was difficult to get to with a truck, but there was water in the vicinity. So you just attach them behind the tugboat, because they are again buoyant, and you just tow them to their final position. The world's largest log gates, these are placed in the Wilhelmina Canal in the Netherlands. They stop a water column out of my head of 9 meters, and if these log gates would fail, Rotterdam would be flooded. As our foreign friends probably know, the Netherlands, most of the Netherlands are below sea level. So this log gate is critical, is absolutely critical. If these would fail, Rotterdam again would be flooded. So we had to demonstrate to various players, for example, also ministries, that this application is safe. So we had to demonstrate that these composite log gates could could survive an impact of an inland vessel, and we take pride in that, to ascertain that our applications are the last in line to fail. So concrete would fail first, then the steel pins connecting the log gates to the outside world would fail, and then only then we are allowed to fail. So these products are extremely safe. And why is that? One of the reasons is composites are more flexible than steel. So most of our applications are designed on stiffness, on deflection, and strength is a result from that. So the strength, safety, reserve factors you get are huge. And for this log gate, for instance, it was the visual aspect that was kind of important, because a log gate could be relatively flexible for its end use and application, but it's the sailor sitting in a sailing boat looking at this log gate that would not feel really comfortable to see a huge deflection on this log gate. So this log gate was made extremely stiff to have the same visual deflection as the wooden or the steel or the concrete variants. Also nice anecdote is these log gates were also buoyant, so we had to add weight in the bottom of the log gate to make sure that they would not float. And because of using these monolithic blocks, or these heavy blocks in the bottom, it enabled us to drill these water flow channels that you see in the bottom. So it's just a matter of drilling big holes through these massive blocks. Then we zoom in on to InfraCore Company. What is InfraCore Company all about? We use the same technology as FiberCore Europe, but we do not use it in bridges and log gates. That's their business. We take care of all product market combinations in other sectors. And we do that together with key strategic partners, and definitely based on the proven track record of FiberCore Europe and on the patented InfraCore technology. And our basic philosophy is we do what we are best at, that's composites, and we cooperate with partners that have additional strengths and knowledge. And again, our technology is available in licensing forms or partnerships. So I come from the maritime world. I'm an aerospace engineer. I have also some degrees in naval architecture, and I've been active in the maritime world for a couple of years. So yeah, InfraCore Company is also heavily involved in the maritime, offshore and inland business. What you see here are a number of applications that we're thinking of. Just look at the pictures. It's edge covers, offshore access platforms, heli decks, also massive hydrogen tanks, offshore platforms. We could do total ships, ship elements, balconies, fenders. What you see here is a non-protected, really basic InfraCore composite structure, which has been subjected to 2 hours of fire testing under structural load, because we had to prove that the structural load capacity of our technology is good in order to be able to install this heli deck on the mega yacht of Steven Spielberg. And this fire test was stopped after 2 hours, not because there was a reason to do it, it's just nothing was happening. So the Fire Testing Institute said there's no reason to continue. This could survive the fire for hours and hours and hours, which helped me, together with my colleagues, to convince, for instance, Meyerwerft, a huge cruise ship builder, to start a project with them, and we developed for them inner and outer composite walls, which should replace the steel bulkheads, but also have in it, so the composite structure should have in the concept, the fire insulation, the noise insulation, the aesthetical finish. So instead of having steel plus fire insulation, noise insulation, aesthetic wall, we developed one fit-all solution. So everything is in our bare composite structure. And we developed a solution which is really impressive in way of fire protection, which enabled us to reach an FRD 60 certificate. What is a FRD 60 for our steel friends? That's the composite equivalent of A60. So it's a structurally loaded structure which can withstand 60 minutes of fire under loading, without a temperature rise which extends a certain threshold on the backside, and with a maximum allowable deflection. So again, without added passive fire insulation, it's just the bare composite structure which has reached this FRD 60 certificate. Another project that I would want to briefly highlight, because I could talk days about this one as well. This is called patch repair of FPSOs. FPSOs are huge ship structures which are so large that they cannot go into dry dock. So the repair and the maintenance should happen on site, so on the sea. And if you want to crop and weld, you need to inert the tanks, which takes weeks and sometimes months, which is a very costly activity. So we were requested by big players like Total and Petrobras and Naval Group to come up with a composite patch repair enabling cold patch repair. So we would just laminate, actually infuse, resin infuse fabrics on the strength deck of FPSOs, so that the strength deck would be nominally performant again, without any disturbance of the operation. Then this project. What I should first state is that we also so the InfraCore composite technology has a specific patent on NACA profiles as well, so we can make airplane wings, wind turbine blades, but also rudder flaps. And we convinced Becker Marine Systems to trust us in developing for them a rudder flap, actually the largest rudder flap that they have sold until now, in composites. So this is the composite rudder flap for the 18,500 TEU container ship. What you see on this slide is on the left, the aft ship, the rudder stock, and the rudder flap. And the rudder flap is the baby that it's a big baby, the baby that we developed. So you start with the design work. So this was also done extensively with finite element analysis. This is just, all these green lights are just showing that we meet all the requirements of rules and regulations. So we have checked all the failure modes and all the allowables for all the inner components of our rudder flap. And it should remain everywhere under 1. You see that we tuned it so that the rudder shell is on 1 because the goal was to make it as lightweight as possible. So the design requirements were met. And what you see on the upper figure is, I think, a good illustration of the flexibility that our technology enables. I said a couple of minutes ago that we place webs in the direction as deemed necessary. So you see webs running in horizontal direction, vertical direction. You see these green areas, that's where solid blocks are placed because those are the higher stresses and strain areas. So we wanted to have additional flesh there. So we just place the material where needed and in the direction as needed. And then we produced a scale 1 to 6 rudder flap because we could well have produced a scale 1-1 because again, size does not matter for us, but you should be capable of testing such a thing. And this rudder flap has, just to give you a bit of a feeling, 100 tons per square meter loading. So it's a heavily loading beast. So in order to test it in an ultimate way, so up to failure, scale 1 to 6 was chosen. And how did we test it? This was tested in Hamburg by Becker Marine Systems. It was tested in a steel rig, and the deflection was imposed by inflating air cushions, the type of air cushions that you could use to lift ships with, or skyscrapers. So really the high heavy-duty air cushions. And the lower right, you see a picture of the rudder flap. So, which brings me to the statement also is, for us, aesthetics is an option. So we can also make the nice polished and shiny composite structures, as most of us know, on sailing yachts and mega yachts. But for us, aesthetics is an option. So Becker Marine Systems agreed with us that this rudder flap should be as light as possible, but as cost effective as possible. So if the steel has an allowable tolerance of ±5 millimeter, let's think of that. Why should the composite be smoother? So we agreed with Becker that it should have the same rough finish as the steel one, which enabled us to produce, to use a very rudimentary mold system, thereby leading to a reduced cost. We could make it polished again, but good enough is good enough, and aesthetics is for us an option. What you see here are some pictures showing the rudder flap under loading. We reached something like 2.5 times the class load. So plenty of safety factors in this design again. So dry testing was successful, very successful. And next step is we will produce a second rudder flap, which will go into wet testing, so that we can validate the hydrodynamic performance of the rudder flap. And also to demonstrate that the actual hydrodynamic loads are 20% lower than the class imposed loads, meaning that, yeah, again, this rudder flap is more than safe enough. Which brings me to the next project I want to highlight. This is a project that we have worked on together with project partners. Work package leader is Damen Naval and Damen Shipyards. airborne composites, Airborne UK, also a composite player. We have Evonik, which is a company, a huge company active in the chemistry. They developed the dedicated resin. We have TNO, who was involved in the testing, which we will show later on. So this was a joint effort, and InfraCore Company was in first instance approached because of the heli deck. You can imagine that if you can make a 60-ton traffic bridge, a heli deck for a ship is kind of similar. But during the course of the design work, we, in good accordance with our project partners, we were allowed to take care of the decks, also the inner decks. So we took care of the strength deck, the heli deck, the inner decks, but also the bulkheads. And the next slide, you will see that we also took care of the joint design. We took care of the assembly, the overall assembly. And we also did the infusion of the hull. Airborne UK did a sandwich hull, and we did an InfraCore hull, which I will show later on. So what was the result of this design work is that Damen did initially a full sandwich ship design, which was already way lighter than the steel benchmark, something like 40% lighter, I think. And we reduced this weight even further by translating sandwich into InfraCore. So the weight reduction was stretched 15% further. I think we have proven to our partners that our solution is not only lighter, but it's also more cost effective, and it has increased robustness as well. The heli deck, I will show later on, was not possible in sandwich technology. It was possible in InfraCore technology. An additional benefit is that by using an InfraCore heli deck, you can also survive a heli crash, multiple heli crashes, which I will show later on, and also a hydrocarbon fire after heli crashes. The heli deck can survive multiple heli crashes and also a heli fire, which was also validated by full-scale testing. So a fire which lasted for more than 1 hour. As said, we also developed a design. And for us, very important is everything we do, we want to do it wherever deemed needed. So whether it's on an FPSO in the middle of the ocean, or we should build a composite ship in a steel shipyard, that's what we want to do. We do it wherever deemed necessary. So we developed joints which can be created, assembled wherever. And we did that at Damen in the steel shipyard. And we want to have plenty of redundancy. So most of our joint designs are based on 3 basic principles. Here in the ship design, we respected 2 of them. So we want to have a shape lock. So even if the connection would fail, it cannot move, it cannot go anywhere. So that's basic principle number 1, shape locked. And 2, chemical lock. So in this case, an adhesive connection. These are basic designs of the ship joints that we have developed. So for the ship, or for the hull deck, the deck bulkhead, the hull bulkhead, all possible joints that can be found in a ship have been designed, have been produced, and have been tested. So on the left, you see first, again, the detailed finite element analysis, and then we produced scale 1-1 joints, all type of joints that were then tested by TNO to prove and validate the design work. So all tests have been, all designs, all joints, all joint types have been tested, and all have survived the ultimate tested with safety factors minimally 6 all the way up to 8, which was nice because it enabled class Bureau Veritas to say that fatigue assessment was not needed of these joints. If you can demonstrate a minimum amount of safety, additional detailed fatigue assessments are not required. And that was reached. Joints are nice, but if you want to validate the full composite ship, you should also go for the global loading. And yeah, scale testing a full ship, that's a bit costly and it's a bit difficult. So we agreed with Bureau Veritas that making a big torsion box, as you see here, would do the trick. So what you see, the upper right picture, you see a cross section of this torsion box, two hillsides, the strength deck, and then in the box itself 4 bulkheads, so that we could put this ship-like structure in a 4-point bending, thereby testing this ship structure in global loading, hogging, and sinking. And that's what we did. And this was one of the most impressive tests that I've had the pleasure of witnessing professionally. We demonstrated that this global design met twice the design load. So the steel frame is there to introduce the global bending. 400 ton of pressure was the design load, and we reached 800. So twice what was requested. Again, plenty of safety. I have some movies to show you what this is. This, for instance, is the design load test. So this 400 ton, that's what you see. And it's kind of funny because I had bets with TNO. I was betting that the steel frame would fail. And in the beginning, they were laughing. They said, "Yeah, Laurent, funny guy." But during the course of the testing, they became a bit more nervous. So it was funny because it was a fair battle, steel versus composite. I will go then to the next movie, which is this one, where you hear the pings, so little pings. Those are just fibers breaking. Imagine that you have millions of fibers in this box. So hearing here and there a little ping, a little fiber breaking. That's nothing to worry about. This is what is happening with this box. So again, nothing spectacular. At the end of the day, after 30 minutes of suffering, there was more noise to be heard, which is understandable. But this lady behaved beautifully under this global design. So very pleased with this result again. And then I go back to the presentation. Let me see. Yes, here, use it again. So we have now already discussed the joints, the global behavior, but what is also nice is to produce a ship compartment in a steel shipyard environment. That's what you see here. And we also needed something to have so that we could do the heli crash testing, the hull impact testing. So this was also the purpose of this demonstrator. And we also wanted to do this really to demonstrate how fast a composite ship can be produced. And I have, again, a movie to show you this. First of all, I will first say something technical again. So making horizontal injections, as I said, for us, size does not matter. When you make large ship-like structures, you have the vertical challenge. Vacuum infusion, resin infusion is done with a 1 bar pressure difference, reaching 1 bar of pressure differential. So for instance, 10 meters in height, that becomes an interesting challenge. So we had to prove within this project that we could inject vertically these large hull structures. And that's what we did. So let me show you this movie. You see here, by the way, also all these connections laying on the floor. So you see now a bit more the size of the scale to one joints. And this was done in 2 days, 2-3 days. So a very small team of people, fully adhesively bonded connections. This is sealing off the cavity so that the adhesive can be injected. because we developed an industrialized way of applying the adhesive. And we did the hull infusion live during a general assembly. So we did not do it behind closed curtains. We did it live in front of 120, 150 people on the hottest day of the summer, by the way. And this is the resin infusion, which took 2 hours. And whether we do this section 1 meter in width or the full hull in one go, it does not matter. So for us, again, this technology is fully scalable. And this is how we reached, I think it was 6.5 meters, but we could go higher. So definitely doing infusions. Let's if you want me to put a figure up to 8.5 meters, that's definitely doable. So again, we did this live during the General Assembly in front of all the Ramses. Ramses, by the way, is a European project where all the biggest European shipyards are involved in, and everybody looked live at this resin infusion. So again, very confident and nothing to hide. And then I want to. No, I think I missed one movie, so let me first show you then the last movie before evolving to the last part of my presentation. This is a movie I thought about impact testing. So let me see if my connection is still going well. Sorry for this. It's still good. I took the wrong one. I need this one. My apologies. So first, the hull was impact tested. That's a sandwich hull made by Airborne UK. And then the strength deck with our technology was impact tested. So what was done here is at the end of the day, we did, I think, 4 or 5 heli crash impact tests on the heli deck with energy levels twice as high as what would occur with a heavy class helicopter, so multiple heli crashes. And it was a success. And then a heli deck structure with damage was sent to Sweden for a hydrocarbon fire test, which I think lasted for 60 minutes. A fire which was more severe, what we understood, than what would occur with a real helicopter fire. And it was easily extinguished after 60 minutes. There again, we proved that it was good. It was good enough. And then I want to finalize this presentation by showing this. A number of companies contacted us a couple of months ago because they were interested in composite inland vessels, composite push barges. And yeah, we want to help our customers, and we see a potential in this field. So we did 4 designs: a 55 meter, 76, 90, and 110 meter. So full composite push barges. So the basic design is done, and I just want to show you the results of 76 and 110. For the 2, half of the structural weight is taking off as compared to the steel. We can take the same cargo load as the steel sisters, but it's simply more lightweight. So it has a more shallow draft, or it can take more payload. And what we did also, it's not only a design, we did also a full cost calculation with the risk analysis. So costing is in place, planning is in place, quotation has been handed over to a number of players, and so we are ready for this commercial project once it has been signed and ordered. That's how I would like to conclude my presentation. Thank you so much for your attention and your time.
Well, thank you very much, Laurent. Very interesting presentation. And we are now going for the questions. So let me show my screen. Yes, that's there. So now it's time for questions. There is a question panel where you can type in your questions, and we have received a few. So Laurent, these cabins the project you did at Meyerwerft with the FRD60 panels, is that for accommodation panels or cabins, or where are these applications going to be used at the ships at Meyerwerft?
It's a good question. So these could be inner walls and outer walls. Inner walls would be for both working spaces as cabins. So the aesthetical wall finish would then be for the cabins, and for the working spaces, the aesthetical requirement is less. So it's a one solution fits all, and it has been developed for two production phases. So both the late stage outfitting phase, so where actually welding would not be allowed anymore on board of cruise ships, so these panels would then be adhesively bonded, so only cold work again, or they could be prefabricated in larger sections, so they could already be installed in the block building stage. So again, also a solution for two potential production phases.
Thank you. And there was a question from Lars Malta. Do you use a special matrix in the matrix to increase fire resistance?
Again, good question. The FRD60 was reached with classical ingredients, so classical glass fibers, a classical resin, a specific foam core material, because the foam core is definitely important in relation to the fire performance, especially smoke and toxicity. So it's not a fancy exotic core material, but it's not the typical foam core that we would use, for instance, in bridges. And there's a special intermediate coating on it, which is well known in the composite world. So I would say for 90% standard materials. For other projects, we investigated special resins, special fibers as well. Yeah, again, it's a bit in our DNA. If it's not necessary, we go for the most cost-effective solution. So for this FRD60, it was not necessary. So, but for other applications, yes, you have to go a bit further.
Okay. And also a question from Lars Malta was the Ramsets project with Damen. What was the weight saved on that segment if you would compare it to steel?
Out of my head, I think we reached, was it 50, 60%? So let's keep it on 50.
50% less weight compared to
steel.
And steel, if you would rebuild that segment in in steel. Okay.
Correct.
Yeah, and you were saying the infusion could go up to 8.5 meters high. This segment was about, what was it, 5 meters wide or approximately?
Yeah, the section was something like 2.5 meters. I didn't include that in my presentation because I had to make choices.
Yes.
But for us, doing an infusion of, let's say, 2.5 meters in width, just as you see in this diamond demonstrator, or we would go for the 110 push barge in one shot. It's the same basic approach. So it's just a modular resin infusion strategy that we just can duplicate. For us, it's just a matter of doing the same trick all over again.
So then you can extend that that segment up to 8.5 meters high, and then 110 meters long, and do the infusion in a single shot.
Exactly. That's
okay.
Correct. That's correct. So you need to how do you say it? You need to be dedicated, to be focused, prudent. But there's no technical reason why you should not be capable of doing the largest infusions ever. Just for your information, in 2014, we already had the world record of resin infusion, which was taken off from us by the wind turbine blades. And we are ready to taking it back whenever we have the opportunity.
Okay, because that brings me to the next question, which is related from René Franke. Is for the example of the barge that you showed, how are the transverse seams between the blocks made, or are there no transverse seams at all? If I just
there are no transverse seams. That baby would be produced in one shot.
Okay.
And we could do it in segments. Don't get us wrong. That's what we demonstrated within the work package of Damen, that we can do primary adhesive connections. It's by doing it like that, it's less risky, definitely, but it's heavier and it's more expensive. So if you have the guts of doing it in one go, you will end up with a more robust, a stronger, a lighter, and a cheaper end product. And that's the emphasis and the target that we set upon us. If we dare to do it, we should do it as light and as cheap as possible for our customers.
But if you have to do it in one, you need to build the whole construction which is supporting this infusion, the mold, let's say. You need to build it as one.
Yes, but yes. And that distinguishes us a bit of the rest of the composite world. Is why make a fancy, expensive mold for a one-off product if it's not necessary? So the mold system for these push barges, without stepping into too much detail, because I want to keep a number of secrets to ourselves. But just to give you an idea of the costs of the mold system for one push barge, it's somewhere in the region of 50 to 75,000 euros for a 110 meter long push barge. So it's very simple. It's reusable, by the way, so we could use the same mold system for different dimensions.
Again and again.
Don't think of fancy, exotic, polished, shiny molds. Good enough is good enough.
Okay. Well, very interesting, and that brings us to, I think, the last question by Marianne Candela is, what is next for InfraCore, and what is going to keep InfraCore from having world domination in this application?
Oof, that's a challenging question. I would say customers who believe in the possibilities of alternative materials. So, it's all about launching customers who are daring to step up their game. I think it's very important that I say that we have nothing against steel. Steel is a beautiful material and is a well-proven material, and there's room for I think in some cases another material such as composites, and combination of the two is in most of the cases the way forward. What will stop us? Yeah, again, daring launching customers, rules and regulations. We have to say it also. It's a conservative world, and we have done an immense work the last years, as you have seen in this presentation, doing full-scale testing and doing whatever possible to show so that people can feel, see what we have said for a long time. But in some cases that's still insufficient. And I can only give an example. Is you know, solar ships, so ocean-going ships. Fire safety is very critical, because if you have a problem, sometimes you are days, maybe weeks away from rescue. So there's a good reason why they are so cautious and careful. But to my surprise, the inland rules and regulations are even more conservative. So you need a lot of perseverance and enthusiasm to keep on motivating you to try to do things differently. And Ruben, you know that as well as I do. It's a pioneering challenge. And challenge also because I know that René Franke is listening, and I saw that he asked a question also today on social media. It was about recycling, so I think it's also important to say that as well here. Steel can be reused, remolten, that's fine. And the perception is with composites, it can't. Let's keep it simple. It's definitely more difficult than steel, but it's not impossible. And I can only refer to time is good for me. This week, Vestas also started a campaign by saying that because they have also this challenge. They have a huge amount of wind turbine blades. What to do with them? They started now a campaign saying that 80% of their wind turbines will be reused in the production of the new generation. So the basic ingredients will be reused again in the new generation of wind turbines. And we at InfraCore Company know very well how it could be recycled. That's one thing. And also keep in mind, I can use the FiberCore Europe bridges as an example. The durability of composites is incredible. The warranty and the lifetime expectancy of these bridges is so big that FiberCore started a new commercial approach. Next to selling bridges, they also lease bridges. So you just rent a bridge for 25 years, and then it goes to a next location and next customer. So maintenance-free products as you have never seen. And for me, the near future, and that will, I think, open the box of Pandora even further for composites, is using green composites, biocomposites. So try to use, for instance, flex fibers for our Japanese friends that are listening, bamboo fibers, which are brilliant. Bio-based epoxies, bio-based vinyl esters, polyesters, making the composite products at the end of the day biodegradable. Is that far away? It is not. I can only refer to, for instance, Green Boats, a German shipbuilder who is making beautiful sailing yachts with already quite impressive dimensions with these bio-based composites. The technology is available. It's just a matter of scaling up. And something that will also challenge, to come back to the question, is industrialize the production. That's what we have done already. But we can go even further. I'm not using the word automation because we prefer industrialization, but having the production technology in place to produce serial lines, huge products in a very industrialized way. That is the homework that we have already performed, but we still have it on our desk, and that will definitely also facilitate the breakthrough. So I hope that answers the question.
Absolutely, and thank you very much, Laurent. We are at the end of the webinar. Was a very interesting presentation. And to thank you for that, Laurent, the KNVTS will offer you a 1-year free membership of being a member at KNVTS. And I also want to thank Marianne, who did in the background all the technicalities to make this webinar work. We do the talking and she does all the technical stuff. It has been recorded and we will share with everybody that attended or who could not attend. Will receive an email with the recording in about 24 hours. And our next webinar on the agenda is June 16th, and it will be talking about environmentally friendly sailing ships. The topic will be building Sabre. It's a wooden sailing cargo vessel. And they are building this literally in the jungle of Costa Rica. And Daniela Doggett will be our guest speaker on June 16. So thank you all for attending the KNVTS webinar. And once again, Laurent, thank you very much for your very interesting speech today. And I want to wish everybody a good evening or good afternoon, and see us next month. Thank you very much. Thank you, Laurent. Bye-bye.
Thank you, Ruben. Thank you. Thank you. Good evening. Bye-bye.
Good evening. Bye-bye.